In this problem, we're taking a look at delivery trucks that are basically leaving Phoenix and are going to all these various locations. So we know that this restaurant has locations in Chandler, Gilbert, Phoenix, Tempe, and Tucson. So I'll just abbreviate Tucson with a U. Now we do have to assume that Phoenix goes to Phoenix because the warehouse is in Phoenix, but they also have a location in Phoenix. So we have a total of 5 locations. Now the question ultimately asks, how many round trips can be made to each of the locations? Okay, well, why don't we let our variables represent that for us? So C equals number of round trips to Chandler. G be the same thing to Gilbert. P be the same thing but to Phoenix. T be the same thing but to Tempe. And U be the same thing but to Tucson in this case, or Oro Valley. Okay, so now we need to consider the different constraints that we have. So starting up at the top, we have 5 different locations. We know the different mileages one way to each of the locations. The company needs to make 1 trip to Tucson. Okay, well that kind of solves it for us, but we still are going to write that as a constraint. So it's a far location, so we have 1 trip to Tucson. So I'll just abbreviate that 1 trip to U. I guess I shouldn't do that since U represents the number of round trips. So to Tucson. Also, there have historically been twice as many trips to Chandler as to Phoenix. So we have to be careful here. So we're going to say C equals P. And we're going to need to put a coefficient here. So is it going to be 2C equals P or 2P equals C? Well, there have been twice as many trips to Chandler as to Phoenix. So to Chandler there have been more trips than to Phoenix. You can give yourself an example. So if there was 1 trip to Phoenix, then how many trips would there be to Chandler? Well, there are twice as many, so there would be 2. If Phoenix had 10 trips, then Chandler would have 20, basically double that. 5 here would be 10 here. So whatever I put in for Phoenix, notice that to get to Chandler I have to double the quantity for Phoenix. So in other words, whatever I plug in per P, I multiply that by 2, that gives me C. I guess I should have written this in words in this case. This should have been 2 times twice as many trips to Chandler as to Phoenix. Kind of wrote that out mathematically already. Further, the insurance contract allows a total of 1,000 miles. So 1,000 miles allowed. And finally, not finally, we need 5 constraints because we're going to need to form 5 equations. Chandler receives half the number of truckloads as Gilbert. Okay, so again, we're going to write out Chandler has half number of trucks as does as Gilbert. And it also says as does Tempe. So Tempe has the same situation, same relationship with Gilbert. So same for Gilbert. I'm going to write this over here. This is getting too close to the bottom. So we have Tempe has half loads as Gilbert. So they both have half the number of truckloads than Gilbert. So Gilbert basically it's more. Well, let's start to write these out as constraints now in mathematical form. So 1 trip to Tucson. Well, 1 trip to Tucson means that U, our variable that represents the number of trips to Tucson, equals 1. So again, we've got to be careful here because U represents the number of round trips. So U is exactly equal to 1. We have twice as many trips to Chandler as to Phoenix. So whatever Phoenix is, double that to get Chandler. So we'll have that. We'll have C equals 2 times P. Additionally, we'll have 1,000 miles allowed total. Okay, well, for each round trip, notice that we're going to, if we're driving to Chandler, we're going to have to basically drive twice 18.2 miles. One time to get there and then one time to get back. So, and depending on how many round trips we take, we'll have to multiply that distance by however many round trips we have. So 2 times 18.2 will give me the distance for one round trip times the number of round trips that I have will give me the total mileage, plus twice 31.3 times the number of round trips to Gilbert. So 2 times 31.3 times the number of round trips to Gilbert. Similarly, we have 23.6 miles to Phoenix, and so we will write plus 2 times 23.6 times the number of trips to Phoenix, plus 2 times 12.1 times the number of trips to Tempe, plus 2 times 108 times the number of trips to Tucson is equal to 1,000. Okay, so all of these mileages need to tally up to as close to 1,000 as possible. Now, we also said that Chandler gets half the number of trips as Gilbert. Okay, well, what does that mean? Well, if Gilbert gets 2 trips, then that means Chandler gets half that, so they only get 1. If Gilbert gets 100, then Chandler only gets half that, so they only get 50. So you can write this one of 2 ways. You can either say to get Chandler from Gilbert, you have to take 1/2 of the number of trips to Gilbert. But you can also go backwards so that you don't have to work with fractions. You can say, well, how do I get Gilbert from Chandler? Well, I notice that Gilbert is always double what Chandler is. So if I double what Chandler is, I get the number of trips to Gilbert. And the same thing holds between Tempe and Gilbert, because it says the same thing holds for Tempe and Gilbert. So basically we just change Chandler to Tempe. If we double the number of trips to Tempe, we get the number of trips to Gilbert. Now the challenge here comes in that we need to write all these constraints so that all our variables are lined up, and so all the solutions are on the right-hand side. So, for example, this constraint right here isn't going to fly because we need to have all our constants on the right, all our variables on the left. So what we're going to do is we're going to try to match up all the variables. So I'm going to start with this equation, since this is a whole equation that involves every single variable in non-zero form. So 2 times 18.2, if I multiply that, I get 36.4 times C, plus 62.6 times G when I multiply 2 times 31.3, plus 47.2 times P, plus 24.2 times T, plus 216U equals 1,000. And so what I want to make sure to do is, with all the other equations, to line up the variables so that I have C, G, P, T, and U. So in the next equation, well, actually our first constraint, we have U equals 1. So what I'm going to do is I'm going to write U. I've got U over here. U is equal to 1. Well, how many T's do I have in that equation? Well, there are none, so I'll write 0T. There are no P's, so I'll write 0P. There are no G's, so I'll write 0G. And there are no C's, so I'll write 0C. And that's a way to create an entire constraint where only one of the variables is non-zero. Only one of the coefficients is non-zero. So U equals 1. Now I'll do the same thing for the next constraint, which is that C equals 2P. So I'm going to actually move 2P to the other side by subtracting it. So I'll have, this will pan out to become C minus 2P equals 0. So my constant is over here, it just happens to be 0. So I have C, I have negative 2P. So I'm going to write 1C minus 2P, and then everything else is 0 because I don't have any G's, I don't have any T's, I don't have any U's, and that's equal to 0 since I moved everything to the left side. I'll do the same thing now, but I'm going to do it for 2C equals G, so that means that 2C minus G equals 0, and 2T minus G equals 0. So I'm going to do 2C negative G equals 0, so 2C negative 1G plus 0P plus 0T plus 0U equals 0, and I'm going to do 2T, which is here, that's positive, minus 1g, 0c plus 0p plus 2t plus 0u equals 0. So there are my 5 equations in all their glory. So now what I'm going to do is I'm going to lift, if you can imagine, here are all the c's, here are all the g's, and so on. So I'm going to sort of lift them out, and I'm going to form a 5 by 1 matrix that contains all the variables, and then I'm going to have a 5 by 5 which contains all of the coefficients of all these terms. So what's that going to look like? Well, that's going to look like this. The first one, we notice all the coefficients are 0 except so C, G, P, T, and U, except the U coefficient. I'm going to make this, give myself plenty of room to write here. And then I'll have 1, 0, negative 2. Oh, excuse me. I think I started on a different equation. Let me start over here. So the first one we wrote was 36.4, 62.6, 47.2. Then we have 24.2, and we have 216. So those are our coefficients for CG, PTU. So let me come back here. So we have C, G, P, T, U. Okay, now we'll do the same thing for the remaining equations. So we have 0, 0, 0, 0, 1 for U equals 1. Then we have 1, 0, negative 2, 0, 0. So that's 3 equations. Then we have 1, negative 1/2, 0, 0, 0. And finally, we have 0, negative 1/2, 0, 1, 0. And that's our entire coefficient matrix right there. It's a pretty hefty one, and you can probably imagine this is pretty hard to solve by hand. That's why it makes matrix form makes it so much easier to do. And then we'll have our C, G, P, T, and U. This is our X matrix, contains our variables. And then our constant matrix, our solution matrix, which contains all the corresponding row solutions. So this guy equals 1,000. I'm going to come back here so we can see where we're pulling these from. So one of them is 1,000, then we have 1, 0, 0, 0. 1,000, 1, 0, 0, 0. So there's our A, there's our X, there's our B. And we know that to solve for X, we have to take A inverse B. Now multiply both sides by A inverse. So what I've done is I've entered that into my calculator. I have the A matrix here, which we mentioned. Some of my rows are inverted, but that's okay. I think I wrote my equation, this equation later on. But I have all the exact same rows. They're all just in slightly different order. However, keep in mind that your 5 by 1 matrix, this guy, the numbers still have to match up. Like this equation still have to match up with 1,000. This has to match up with 1, and the rest with 0. So you can switch them around, but you have to make sure that you switch all the rows. So then what I will do is maybe I'll just go ahead and, no, that's okay. So what I'm going to do is I'm going to do A inverse matrix B. Now, again, my values are a little switched, so let me identify these for you first. So my X matrix is going to be X equals, and so my variable order is, should still be the same actually, CG, P, T, U. And my outcome is 3.7, 7.5, 1.9, 3.7, and 1 trip. So if I make this many trips to each of these locations, then I can definitely satisfy the constraint. Now I've got to be careful here. You know, of course, now the company, we won't analyze this in any more detail, but we'd have to figure out what would happen if we rounded these differently. So the simplest solution would probably be to round most of them down, except the ones that are really close, and say, you know what, we can do anything less than this under budget. But depending on, you know, do you want to have more trips to Chandler, or do you want to have fewer trips to Chandler, like 3 versus 4, then you can kind of decide how many of each of these trips you want. But we'll just go ahead and stop here and say, now it would be a time to analyze it and say, what's the best that we could do?